Entonces, the next talk is from Dr. Rolf Hyde. He's already logging in the session. So please, Rolf, if in the meantime you could just share your presentation. Well, let me introduce Dr. Rolf Hyde. He got his PhD in 1991 from the University of Karlsruhe in Germany. From 91 to 99, he was working as in several postdoc positions and also as a guest scientist in different places around the world, like for example in the Ohio State University in the United States, in the Max Planck Institute in Dresden in Germany, and also in the University of Regensburg also in Germany. From 99 to these days, he's been working as a senior scientist in the Institute of Solid State Physics in the Karlsruhe Institute of Technology, KIT, in Germany. And since 2017, he has been working as a deputy director in the Institute of Quantum Materials and Technology, also in KIT in Germany. So please, Rolf, could you share your presentation?
Yeah, thank you, Omar, for this nice introduction. I have at the moment a problem with my camera. It seems not to work, although I switch it on. So I can start with the presentation and see if that at least works.
Yeah, sure.
So I have to log in again. I will see if that presentation is up.
Okay. Okay, the presentation
you see?
Is working. Yes, could you please use the full... that's great. And we also are able to see you.
Okay, now my camera works finally. Good. Very well. Okay, thanks again, Omar, for this nice introduction and also for the invitation here to give a talk at this School of Superconductivity. And also greetings here from Germany, where it's already dark. And I apologize also from the beginning that we'll turn away a little bit my head because I'm looking mainly at the big screen here, second screen, where I can see my presentation somewhat better. So I want to give now a talk about more recent work we have done and in collaboration with a group of in Spain. My talk will essentially be twofold. The first part will be a kind of introduction to the theoretical or computational techniques which are nowadays available to address now superconducting properties in general, and which are based on the calculation of electron-phonon interaction. And in particular, then I will apply these techniques to a specific type of situation where the superconducting material is in certain confined geometries, namely to thin metal films. So let me try to go on. Start first with the motivation of my talk. And this first slide is very similar to the one you have seen in the previous talk. So there has been a recent comeback of phonon-mediated superconductivity due to the discovery of these hydride materials, which show extremely high transition temperatures, but albeit at very high pressures. And for a long time, actually, the so-called conventional superconductors has been studied over many years until the high TC compounds, the cuprates, has been found. And only very recently now this comeback of phonon-mediated superconductivity has been revived this field due to this discovery of the hydrides. A second interest in electron-phonon interaction in more general has come from applications to low-dimensional, or in particular two-dimensional materials, where one has found that the electron-phonon interaction shows some peculiarities if they apply to this kind of low-dimensional materials. In particular, then thermal transport, electric transport, or optical properties have to be modified, and one tries now to understand the specific features which are quite important if one wants really to use these low-dimensional materials in certain devices. Now, as you may all know, electron-phonon interaction is one of the fundamental properties in materials. It affects really in a fundamental way quasiparticles, both electronic and vibrational quasiparticles. and it provides the clue for superconductivity. So this is the so-called phonon-mediated effective electron-electron interaction, as the previous speaker has very nicely outlined in his talk. Electron-phonon interaction affects a lot of physical phenomena, in particular transport properties. It's on the heart of phenomena like charge density waves or excitons, and it provides this clue, as I mentioned before, for superconductivity. And in my talk, I will focus on this aspect of the electron-phonon interaction. Now, on the right-hand side, let me just switch the pointer here. On the right-hand side, you see a sketch of this electron-phonon vertex, which is the basic quantity we want to calculate, and which describes the scattering of an electron with momentum k to another state with momentum k plus q by the absorption or emission of a phonon with momentum q. And in true materials, this property is very complicated. It may depend not only on the momenta of the electrons and phonons, but also on band indices or labels for the phonon branches. But nowadays, there are quite very powerful numerical tools available, which are based on density function theory, which allow, in a perturbative approach, the calculation of the various quantities we need to evaluate this property, namely electronic and phononic properties in quite some detail, and the full momentum structure of this vertex. And these tools are really material specific, so they can also provide some predictions for some materials, and one can use them for search of other materials with desired properties. Now let me come to the outline of my talk. In the first part, I will present the computational approach, which is called density function perturbation theory. And then I will briefly and very quickly explain how then the fundamental quantities like quasi-particle lifetimes and the quantities needed for the description of superconductivity are calculated. In the second part, then I apply this to a specific type of problems, namely superconductivity in confined geometries. And there I distinguish two different kinds. The first one is looking at thin metallic films, in particular here thin lead film, and we'll discuss a little bit how the confinement of the geometry here leads to some quantum size effects, which also can be seen in superconducting properties. And then I go to the ultra-thin limit of such films, namely to single atom layers on an insulating or semiconducting substrate, and I will discuss several cases of that in more detail. Let me start with the computational approach. As you may all know, the basic ingredient one needs to understand vibrational properties in solids is the so-called lattice dynamics in harmonic approximation. And the basic quantity needed here are the so-called force constants, which are the generalized spring constants in such a crystal. And in practice, they can actually be obtained by the second derivative of the total energy of a system with respect to atomic displacements, which provide the perturbation of the ideal, otherwise idealized crystal. Now, the Fourier transform of this dynamical matrix is the Fourier transform of the force constants are the dynamical matrix, which then, by diagonalization, provides the basic quantities of the quanta of vibration, namely the phonons. And this is the eigenvectors, which are the displacement pattern of the phonons, and the eigenvalues, which provide the frequencies of the phonons. Now, how can these quantities be calculated within a density functional based approach? This is very briefly sketched now on this and the next slide. So if in density function theory, essentially one is dealing with the Concham equation and one has to solve them, which are essentially wave equation for single particle electron wave functions, which are kind of moving in an effective potential. And this effective potential is here described by a sum of two ingredients. One is the external potential, which is in a bulk, for example, is given by the interaction of the electrons with the ions. And the second part, which is then the screening part or hard-rate exchange correlation part, which is a specific feature of the DFT, and which is a function which implicitly depends also on the density itself. So one has to solve these equations self-consistency. If there is now a perturbation put on top of it, like, for example, introduced by a movement of an atom away from its rest positions, then that induces a change in the external potential. But on the other hand, it also induces a change in the density of the system. And therefore, one gets an additional contribution to the change of this effective potential coming from this screening part. And the change in the density itself can be calculated within a simple first-order perturbation expansion expression, which also depends then on the perturbation of the potential, namely the perturbation of the effective potential. And so we end up with a kind of also a set of equations which have to be solved self-consistently. But on that way, then one gets information about the first-order change of an effective potential and of the density when we imply a perturbation, which for example, is given by a movement of an atom. And now one can carry that further on to the derivatives of the total energy. One example of such a derivative is given by the forces, which are given by the first-order derivative of the total energy. And there's a famous Hellman-Feynman theorem, which in the context of density function theory states like that this quantity can be obtained by calculating just the ground state density, and one has to know the derivative of the external potential only. And only in higher order derivatives, then the first order change in the density enters, and therefore the first order or linear response of the density is sufficient to calculate second order derivatives of the total energy, and therefore one can access these force constants by this kind of linear response calculations. A nice feature of this scheme is that one not only gets now the information of the force constant, therefore on the harmonic phonons, but at the same time, this procedure provides the first order variation of the effective potential, and that is all we need to calculate now this electron phonon vertex, which gives a probability for this scattering event of an electron by a phonon. And here actually the screened vertex enters, and that is the quantity which is then actually needed in most of the properties which are now following. So this scheme really provides an in-depth approach to calculate this vertex function in its full complexity, including the momentum dependence and the band indices dependence, for example. Here is now the first application of a quantity which can be calculated within this scheme. That's, for example, the phonon self-energy. And this represents such a kind of process where a phonon, so to say, is virtually decaying into an electron-hole pair. And the imaginary part of this quantity gives us the line width of a phonon, which is in principle a measurable quantity. And in this formalism, this is just given by a sum, or actually an average of this electron-phonon coupling vertex matrix elements squared over electronic states at the Fermi level. The second quantity, which is now more relevant for the remainder of my talk, is the phonon-mediated pairing within the Eliashberg formalism, which has been very nicely outlined by the previous speaker. And as he also mentioned, that the central quantity at the end we would like to have is the so-called Eliashberg function, and that can be expressed now in terms of these quantities I just introduced, but it's just a simple summation here, where these line widths enter relative to the phonon frequencies. And the integral, the special integral of this Eliashberg function gives then the so-called coupling constant, which is a dimensionless constant defining the strength of the coupling of the overall system with respect to the superconducting pairing. On the other hand, as also shown in the previous talk, this Eliashberg function then enters the Eliashberg gap equation, and by solving this gap equation, one can, for example, extract information about the superconducting transition temperature or the superconducting energy gap. Another quantity where the electron-phonon coupling enters and which plays a little bit of a role in my talk is also the electron self-energy as obtained by exchange of a virtual phonon. And don't bother about the formulas here, but essentially one can evaluate this diagram and obtain expression for the line widths of the electronic state in such a form where here also a kind of state-dependent spectral function enters, which is essentially given again by an average over certain electron phonon coupling matrix elements. And this expression essentially describes the virtual process. If you, for example, create a hole in an electronic band, and by virtual hopping of electrons from other bands or other places by simultaneous exchange, emission or absorption of phonons, that leads to a kind of finite lifetime or inverse line width of this electronic state, which can be expressed in this form. And this allows to also calculate the specific properties related to a single electronic state, and one can also define in a similar way a coupling constant, which is now depending on the specific electronic state one is looking at. And this is also a quantity I will show later in my talk that is accessible experimentally and therefore can be principally compared with theoretical predictions. With that, let me switch now to the first application of these techniques. I look now to the case of thin metallic films, and in particular, I would like to discuss thin metallic lead films. Now, lead as a bulk material, as you may know, is one of the elemental superconductors, which belongs to the family of strong coupling superconductors. It has a very large coupling constant of 1.55. Tc is moderate with 7.2 Kelvin, but lead has been actually central in validating the Lierschberg theory. Namely, already in the 60s, one was able to extract experimentally from tunneling experiments this spectral function, the Lierschberg function alpha squared f, which is here shown from one of the famous experiments by Macmillan and Rowell, shown here by these blue dots, blue circles. And this is now compared with some calculations done more recently for lead, using the spin-orbit interaction included in the full formalism. And this is given here by the red curve, which shows a very nice agreement with this experimental data. Now, without spin-orbit coupling, which is then here this black line here, one sees clearly deviations to the experimental spectra. And also the coupling constant is significantly smaller than in the case we include the spin-orbit interaction, which then gets close to the values which has been extracted from experiment. And that shows that for lead, which is heavy metal, this inclusion of spin-orbit interaction is really very important to describe the pairing and the electron-phonon interaction in this material on the quantitative level. Now I come back to the films. Now, why these lead films have been so interesting? Now, for many years, actually, experimentalists have been able to grow very thin lead films with a reasonable, relatively large extent, lateral extent. You see here a picture from STM, which is, shows that there are lead islands grown on the silicon 111 surface, which extend to several nanometers wide, but they are very thin, namely only 8 monolayers thin in this case. And the high control of such islands, which are essentially atomically flat, allowed then the study of the superconducting properties of such islands in very detail, in particular as a function of the monolayer thickness. And one has found that, for example, in this tunneling spectra, which shows essentially the superconducting gap, that this gap is reduced when you go to thinner and thinner films. Similar, the transition temperature, superconducting transition temperature, also reduces from the bulk value to lower values if you go to thinner and thinner films. Now, this trend has been observed, although you can see here that the scattering of the data is quite large, but there has been another nice observation, and namely that you see when you look at the transition temperature at some smaller, lower, or thinner films with monolayer thickness of here in the case of between 14 and 28, you see actually that the transition temperatures has a kind of oscillatory behavior before it finally starts decaying. And the question was where this oscillatory behavior is coming from, and one origin has been already pointed early on that this might be due to the quantum size effect in these very thin films. What is that the basis for? So in these very thin films where you have a kind of a confinement of the vertical motion of the electrons, that leads to a kind of quantization of the electronic states due to this confinement, and that results in a kind of so-called quantum well states, which then have some kind of quantized energy levels. Here are, for example, measurements, various measurements actually taken together in this diagram of electronic states at the gamma point of the surface preon zone of these films, and as a function of the monolayer thicknesses, so for various different types of films here collected. And you can indeed see if you go from, for example, 6 monolayer to 7, there is a kind of change in these energies, and it seems to show kind of oscillatory behavior. So interestingly, density function theory can very nicely catch this trend. The calculation of density function theory are put here on top of this experimental data as this crosses, and you see very nice agreement in at least in this area closer to the Fermi level. Now, these calculations have been done without spin-orbit coupling, so we have been actually worried that spin-orbit interaction might change this good agreement, but calculations including spin-orbit interaction does not really shift these electronic energies much, and so we have still the similar type, good type of agreement. Now we have essentially applied this machinery of calculating electronic properties, phonons, and the electron-phonon interaction to these different types of films. And this is here now the result for one of these cases, namely for 5 monolayer films. So we have 5 layers of LED stacked on top of each other in a 1-1-1 geometry. And on the left-hand side, you see the corresponding electronic band structure. Actually, there are two plots on top of each other, a black and a red one, and the red includes the spin-orbit interaction, while the black one is the so-called semi-relativistic calculation without spin-orbit interaction. Here you see that the electronic structure actually is very similar for these 2 cases. And here we see also very nicely here, so to say, separate bands, which are kind of mimicking this existence of these quantum well states at the gamma bar point. And in this case, you see actually one of these very flat bands close to the Fermi level, which leads to an increased density of states here at the Fermi level. And that is a kind of importance for the superconducting properties. Now, the second calculation shown here, these are the phonon dispersion for these 5 monolayer films. And again, there are 2 plots, one with spin orbit and one without spin orbit coupling. And the one with spin orbit coupling are the red ones. And these are here compared with experimental data, namely these phonons of such very thin films can be measured with the so-called helium atom scattering technique, which is a very sensitive technique to detect and analyze the vibration properties at surfaces. And here you can see several phonon branches related to this film. And in particular, if you look at the upper part, you see here 2 branches which are reasonably nice correlate with the prediction from theory. But only some of the agreement is definitely better if you include a spin-orbit interaction. And finally, having all these ingredients and including now the calculation of the electron-phonon coupling, we can calculate the Eliashberg function, which then describes the pairing interaction in the context of superconductivity. And here you see, now just look at the red curve where the spin-orbit coupling is included. Indeed, a very strong coupling, particularly a coupling very strongly to modes with relatively low energy. This is the scale of MeV here, the phonon frequencies of MeV. And what you can see is the overall coupling strength is actually 2, which is even larger than in lead bulk. And one of the features we have been analyzing this in more detail comes due to the enhanced density of state at the Fermi level due to the presence of these quantum well states. And the next slide shows now a kind of summary of several of these calculations. So we have been looking at slabs from 4 to 10 monolayers thick. For 10 monolayers, already the calculations become quite demanding. And but we can see that the coupling constant now for the monolayer shows indeed this kind of oscillatory behavior, and it mimics the behavior of the density of states, so which is due to the presence of these quantum well states. However, this variation is actually enhanced, so this is not the only explanation that you can nicely see here, this variation, but also the strength of the coupling matrix elements follows a similar variation, actually. And when one plugs that in now into the equation of the Eliashberg gap equation, you can also extract prediction for transition temperature, and then you also see that this oscillatory behavior also transforms to the transition temperature as a function of the monolayer thickness. Here's actually the bulk value, so you can see that you have this oscillatory behavior, but what you don't see is a reduction of the transition temperature as seen in experiment. We believe, or I will show some arguments, that the reason for that is, or at least one reason for that is given by the fact how we calculate, do this calculation. We have done this calculation actually without taking into account the substrate. So we have indeed taken just the number of monolayers of lead taken together and built this kind of so-called free slabs where vacuum is on top and on the bottom, and performed then all the calculation for these kind of free slabs. And that means that we have essentially completely ignored the substrate. And of course, the substrate will become more and more important the thinner the layers become. And at least a little bit to mimic the presence of such a substrate, what we have done is that we have performed similar calculations, but keeping the lowest layer of such a slab fixed, so to say, keeping them immobile and taking the mass to infinity. And then repeat all the other calculations of electronic, harmonic, and electron-phonon coupling properties. And we find then finally out in this kind of so-called fixed slab geometry that indeed the coupling is reduced compared to the free slab, and we still see this oscillatory behavior. And overall, one has also sees that now there is a small trend of reduction of this coupling constant when going to thinner layers. So we believe at least this neglection of the substrate there seems to be one ingredient which is missing in the previous calculation, and therefore which is needed also then to understand the decay of a TC when going to thinner slabs. Now, a last slide to this topic I show here, and that is now related to the fact that one can also use do photoemission spectroscopy on this type of thin metallic films and analyze certain electronic states. And in particular, one can measure the line width of such an electronic state as a function of temperature. And the data are shown here in the case of a 5 monolayer lead film on silicon 111. And you can see here a nice linear behavior in some temperature range of this line width. And one can show that actually the line width contribution coming from the electron-phonon interaction should have a kind of linear temperature dependence. And the slope of this temperature dependence is essentially proportional to the coupling constant of this individual electronic state. So therefore, from this type of experiments, one can extract directly the corresponding coupling constants. And that has been done, and we have, and these are shown here by the full diamonds here. And we have also then tried to compare that with calculations based now on these certain specific states at the gamma point as has been measured here. And we find a somewhat slightly different behavior. So you see that the coupling, as in experiment, is significantly reduced compared to the coupling strengths we have found for the superconducting properties. So these specific individual electronic states have a smaller coupling. However, we have still some mismatch with compared to the experiment. However, also that the experiment could not really done systematically for 4, 5, 6, 7 monolayers. So therefore, we have not information from the experiment if there is such an oscillatory behavior really existing as it's predicted here by the calculation. But still, somehow we are in the right ballpark of the coupling strength as compared to the experiment. With that, I would like to switch a little bit gear and come to my second part of applications, namely to the so-called ultra-thin metallic layers. And I will present here 3 different cases which have been studied experimentally and where we have also looked from a theoretical point of view. The first one is now, so to say, the ultimate limit when you reduce the number of layers in the thin films to a single layer. Now, what is happening, of course, in this case is that you really get a specific kind of structure of this single atomic layer, which is really tightly bound to the surface. Shown is here one of the phases which have been observed, which is the so-called 4/3 monolayer lead film on a silicon 111 surface. So you see the silicon atoms here below, and seeing then the lead atoms here sitting on top. 3 of the 4 atoms are sitting here close to a silicon, and they make essentially a covalent bond to the silicon on top of the surface. And then as the 4th lead is sitting here in between in this hollow side, and they build essentially some kind of metallic bonds to the neighboring lead atoms. There have been other structures observed of different types and also of different coverage. So indeed, this 4/3 monolayer means that you have 4 lead atoms in the same area as 3 silicon atoms. And the density of this layer is actually even larger than by 5% than the density of lead atoms in a 111 layer, for example, of bulk lead. And of course, for this type of structures, really the details of the bonding to the surface really matters. In particular, this bonding should then capture the saturation of the dendrin bonds of this silicon 111 surface. And as I mentioned, one can have several actually competing structures which may have different properties and stability. Now, the surprise actually came in this work that these single atom layers are still superconducting. So you can see here the measurements of the gap as a function of temperature, showing that you have a transition temperature in this case of 1.83 Kelvin, and here from a little bit lower, 1.5. So that is really was coming as a surprise that the superconductivity survives this limit. The idea now, or the goal of our investigations was now to try to identify the important factors which are somewhat important to understand, which will lead to this kind of specific kind of pairing interaction, which still renders these single atomic layers superconducting. Now here is shown some of these theoretical results we have obtained. On the left-hand side, you see a calculation of the electronic structure of this specific so-called 4/3 monolayer structure, and we have been focusing on this type. And you see that here is somewhat the top valence band of the silicon, and the conduction band is somewhat here up. And in this semiconducting gap of silicon, you see now a variety of electronic bands which are coming from the lead, and which renders essentially this surface layer metallic. And so you can do this same analysis. You can look at the density of states, for example, as a function of energy. We have also compared, in this case, calculations between spin-orbit interaction and non-spin orbit interaction to see the effect of the spin-orbit interaction on the various properties. And in this case, we find actually a reduction of the density of state when one switches on the spin-orbit interaction, which is due to the occurrence of these kind of hybridization gaps in these metallic lead bands. We have then performed also the same machinery as before and calculated finally the electron, the Leerschberg function, which are shown here. And you see that there are certain contributions and certain peaks coming from certain phonon modes at lower energy, and also some high frequency modes which are due to the silicon vibrations. Here's shown the phonon dispersion, where you see essentially certain flat bands, which are all due to the lead atoms lying on top of this silicon surface, and the silicon vibration are shown here by this kind of gray background, which reach much higher frequencies. Now, a little bit the surprise came when we did this calculation then, that actually when one looks at, one does this calculation without spin-orbit interaction, one finds a reasonably large coupling constant of 0.86, but this is significantly reduced when we switch on spin-orbit interaction. And partly the reason is the reduction of the density of state, as I mentioned before, and another one is actually that the photon frequency of the lead vibrations at the surface become actually harder when we switch on spin-orbit interaction. Now, our calculation without spin-orbit interaction agrees relatively nicely with the previous work by Nofsinger and Cohen, where we find a similar lambda of 0.72. But if we switch on really the spin-orbit interaction, lambda is really small, and this is definitely too small to explain the observed experimental superconducting transition temperature. So we've been thinking what could be the reason for this underestimation of lambda. And we have gotten one hint from the experiment. This is an upper spectra also from the work from Sang and co-workers, where they showed some of this kind of band, in particular here this silicon band, a valence band, which has here some on the top of the valence band. And you can see in this case, this valence band actually sits somewhat below the Fermi level. We cannot really say how much, but in our calculation, this top is really right at the Fermi level. So we don't know actually why this is if that's a failure of the calculation itself, or it's due to some specific experimental condition that raises maybe some kind of doping effect, which raises here the Fermi level in the experiment. So we have been trying to look now at the superconducting properties under the condition that we raise here this Fermi level, so by 100 MeV, so a small amount, and then we have redone the calculation of the coupling properties for this situation. And indeed, then we find a significantly increased coupling constant of 0.77 in the case of spin-orbit interaction included. And this is definitely enough to explain the experimental transition temperature, namely estimates based on the Leerspach equation range then from 1.7 to 2.0. So it seems that this kind of very special experimental condition helps somehow to increase here the superconducting transition temperature. We can also go a step further and compare our calculations with helium atom scattering experiments, where they indeed could see very nicely some of these vibrations due to the lead, which have been shown here, indicated here by these filled symbols. And because we have here nicely corresponding calculated phonon lines here, of phonon dispersion, we can nicely assign now the experimental peaks to specific vibrational types, and we find that this one is, for example, a vibration of the lead atoms vertical to the surface, whereas these are vibrations in plane, longitudinal vibrations, and the fact that these vibrations actually can be observed in helium atom scattering also points to the fact that it should have a reasonably large electron-phonon coupling, which has been also coming out from our calculations. So we find a nice agreement with this type of experiments. With that, I switch to the second example. That's indium on the silicon 111. So instead of lead, one can also put indium on top of it. Indium is also an elemental superconductor, but with a smaller TC of 3.4 Kelvin. It has also smaller coupling than lead, namely 0.9. It grows into a slightly different type of structure, which is called a 6/5 monolayer structure, and has a kind of rectangular shape. But it shows actually also superconducting properties with even higher TC than the lead case, namely 3.18 Kelvin. There have been then later on in the literature a kind of discussion if one is here really dealing with a single atomic layer, and there have been also the proposal that actually we have two layers of indium on top of it, which has the same type of symmetry and which are responsible for these superconducting properties. And we have been therefore looking with our computational tools on both of these type of predicted structures, and did the analysis of the phonon spectrum and electron-phonon coupling spectral function. And what we see is there is indeed a difference between a one and a two-layer system. And in particular for the two-layer system, there are more modes in the lower frequency range, which show a much stronger coupling. And the reason for that is that you have in a single monolayer a stronger coupling binding to the silicon atoms itself, which are not so preferable for this type of coupling for the superconducting state. And if we compare now the corresponding coupling constants, we see that for two monolayers we have almost one, whereas for one monolayer we have only half that value. And only the second one is sufficiently large to explain the observed TC of about 3 Kelvin. So in that respect, also these calculations indicate strongly that we have indeed in the experiment a 2 monolayer system, another 1 monolayer system present. We can go also further on and compare that with ARPA's data taken on such systems. And you see here that the ARPA's data, which are given here by these stars, if one compares that with the band structure of a 1 layer system, and here the red or the light red bands are indium type of bands, you see hardly any agreement here in this case, but here you find nice agreement with many of the calculated bands. And so also from this calculation, we would say the experiments really is measuring a 2-layer system. We could also go further on and look at the individual coupling strengths of certain electronic states close to the Fermi surface. And we have done that in a kind of extensive way, but from the experiment, we only get the information that the coupling of some state in the vicinity of the Fermi level should be of the order 1. And we find, of course, a variety of coupling constants ranging around this lambda equal 1 value, but with a quite some large spread. But in that sense, we are still in agreement with the observed coupling strength in ARPA's. And the third and final system I would like to discuss is a variant of the first one I've shown, which is a kind of 2-dimensional alloy on top of the silicon 111 surface. In that case, the previous 4/3 monolayer lead structure is modified in such a way that the lead atoms in a hollow side of this silicon surface are replaced by thallium atoms. And this can be done experimentally in a very well-ordered fashion, and has been then analyzed also by ARPA's measurements shown here, where they nicely see Fermi surfaces of these very ultra-thin or single atom layer system. And they have been also measuring different types of electronic states and also their corresponding coupling, which they show that depends indeed on the band itself, but also on the bands with different spin momenta. Namely, they have also observed here a nice Rashba splitting of the bands due to the existence of strong spin-orbit interaction coming from lead and from thallium. And this system is also superconducting with a transition temperature of 2.25 Kelvin. So even higher than the one seen for the plain of the pure lead case. And when doing now the calculation for this system, we find indeed even a larger coupling of lambda, which is somewhere in between the bulk value for thallium and for lead. A large contribution for the coupling comes from the metallic layer. The substrate is only contributing a little bit in this case. And we find again a very strong coupling to low frequency modes. And based on this kind of calculated alpha squared F, we estimate TC of 3.5, which is somewhat larger than the experimental one. We've also looked at the hypothetical system, namely just replacing all the lead atoms by thallium. But then we find that the coupling really drops significantly, and the main reason is that this thallium, which is the neighboring element to lead, that essentially reduces the number of electrons in the system, and that leads to a shift of the Fermi surface in the system to a region which is unfavorable, where the density of state is significantly lower, and that has immediate impact on the overall coupling strength. So we would not expect that a pure thallium layer is superconducting. Finally, we have also been looking in this case at the electronic structure. We also see the splitting of these bands due to the spin-orbit interaction, and looked at the various states and their coupling. And we see a really large variety of coupling strengths depending on the position, momentum, and also on the band index of the states. But comparing, so to say, the overall magnitude, we see that we are somehow in the ballpark of the one which has been estimated from the photon emission spectroscopy in the system. So in the range of 0.6 to about 1.6, also our values align. So in that sense, we are in kind of a quantitative agreement with the experimental observations. With that, I'm at the end of my presentation. I would like to summarize now the main topics. The first one is I wanted to show you that nowadays these tensor functional perturbation approaches which are based on the density functional theory, are very powerful tools to calculate electron-phonon coupling related properties in quite some detail, and they provide quantitative, microscopic, and material-specific insight into these quantities. And that allows to look in very much detail onto the quasi-particle randomizations of systems and the effective phonon-mediated interaction. And I've shown you some examples of such studies where we looked at the electron-phonon coupling and superconductivity in confined geometries. We have shown us that also these kind of quantum size effects can be somehow transferred to superconducting properties due to the confinement of the vertical motion in thin metallic films. And we have also shown that in ultra-thin limit, even these kind of single atom layers of metal atoms can indeed provide sufficiently large couplings that they become superconducting, and we could then, so to say, specify or characterize in more detail what type of modes are contributing to this coupling and under what conditions it might be derived, might be vanishing this property of the coupling concept. But last but not least, I would like to acknowledge my collaborators. So most of this work I have presented actually has been performed by Irinas Liadneva, also in collaboration with Eugene Julkov and Pedro Echenique from Donostia International Physics Center in Spain. And I also enjoyed collaboration with Giorgio Benedict from Milano, who is an expert in helium atom scattering and their theoretical description and analysis, and he provided also a lot of insight how to understand and interpret these measurements. With that, I come to the end of my presentation, and thank you very much for your attention.
Okay, let's thanks Dr. Rolf Haidt for his presentation. So I don't know if here in the audience there is any question for Dr. Haidt. Or online, I don't know if there is any comment or question. Okay, ahora please.
Yeah. Hello, and thank you, Dr. Haidt. It's more a curiosity. In your slide 17, you show the band structure of the 5 monolayer LED, and it shows like a big band gap on the occupied states. And I was just wondering if this would have like some relevant meaning, or is just because lead is a heavy metal?
When you refer to a band gap, what do you mean? This one here?
I mean in the band structure, I mean in the occupied states, the one that shows in there. Mm-hmm.
Here? Well, this is a kind of a band gap because you have somewhat lower lying localized electronic states here, and they kind of a little bit separate from the more itinerant states here. But that's a main physical insight here. So you see also energies, we are quite already deep or far away from the Fermi level. So these are 6-7 eV. So this is mainly somehow that you have here in LED, you have some S states which are somehow lower lying, and they are a little bit separated in energy from the more SP-like states which are itinerant.
So it would have it doesn't have any relevance, right? I mean for superconductivity.
No, for these physical properties of LED, it does not have really any relevance because the main play is the game is essentially played close to the Fermi level. Well, you have if you look at transport properties and so on, then that doesn't play any role.
Okay, thank you very much.
You're welcome.
Okay, is there any more questions from the audience online? Or in the meantime, they are preparing their questions. I have one question, Rolf. When you explained that for the LED system, this LED system with several layers, in particular this one, and you find out that you have to fix the first layer in order to be as close as possible to the experimental results. What could be the physical meaning of, by fixing this layer, why the electrophonon coupling is reducing? Is because you are breaking the symmetry of the, so to speak, axis of ground of the layers, or you are confining some phonon modes, or what could be a simple explanation or reason why the electron phonon coupling is decreasing?
Now, why it's decreasing? Essentially, you're taking out a little bit of a decrease of freedom here, of course, because you make the lowest layer immobile, but also you change. Well, the idea to take that immobile is actually kind of to simulate a kind of stronger binding of the lower layer to the substrate. And typically, this binding takes somehow away a certain degrees of freedom, which then contribute to the superconducting pairing, and that then reduces these coupling constants. So it has an effect on all kinds of properties. It also the position and the effect of the quantum well state is slightly changed, but you change to what is larger extent, of course, the phonospectrum here. So all these ingredients are playing somewhat contributing, and also electron phonon coupling of the lower layer is then completely taken out here.
Thank you. Another question or comment? Well, if not the case, let's thank Dr. Hyde again.